Unit 2, Day 5, Complex Numbers Continued. This is Mr. McGough. Today we're going to go over some more on complex numbers. So first, a bit of review for solving a quadratic equation. First, to solve, we can either multiply x plus 1 times itself, or square it, and then multiply by 5, find that, and then subtract 120 to set it equal to 0, or we can start right off by dividing both sides by 5. So here we now have x plus 1 squared equals 24. X plus 1 squared is x squared plus 1x plus another x plus 1, which equals 24. And we do that, of course, by x plus 1 times x plus 1. And do our FOIL method. Oops. So, x squared plus 2x plus 1 equals 24, and then I will subtract 24 from each side. And I get x squared plus 2x minus 23 equals 0. For the quadratic equation, I need a, the coefficient of x squared, which is 1. I need b, the coefficient of x, which is 2. And I need c, the coefficient of x to the 0 power, or the constants, negative 23. The quadratic equation states that the roots for x, or the places where x will equal 0, are negative b plus or minus the square root of b squared minus 4ac divided by 2a. So we'll plug in our numbers. So b, again, was 2, so we have negative 2 plus or minus the square root, b squared is 4, minus 4 times 1 times negative 23, or minus 92, which would be minus 92, so plus 92. All divided by 2 times a was 1. So now we have negative 2 plus or minus the square root of 96 divided by 2. I don't see a square root of 96 in any of my answers, so I need to factor 96 to find its roots. So 96 is divisible by 2, which goes in 48 times. 48 is divisible by 2, leaves us with 24. 24 divisible by 2 leaves us with 12. 12 is divisible by 2, leaves us with 6. And then we get 2 and 3 as factors for that. I need to pull out factors in pairs, a pair of 2's and another pair of 2's. So the square root of 96 is the same as 4 times the square root of 6. So I have negative 2 plus or minus the 4 radical 6, all divided by 2. Negative 2 divided by 2 is negative 1. I keep my plus and minus. And 4 radical 6 divided by 2 is 2 radical 6. So my answer is C. Vocabulary. I times I. Anything times itself is I squared. As we know, I is the square root of negative 1. So if I take the square root of negative 1 and I multiply it by itself, or square it, I've undone the square root, so I get the number inside, which is negative 1. So I to the first power is the square root of negative 1. I squared is negative 1. I to the third power, well, that would be I squared times I to the first power, which is negative 1 times the square root of negative 1. I to the fourth power would be I squared times itself, or I to the third times I. Whichever way you go about it, it's negative 1 times negative 1, which is positive 1. For our sample problems, we're now going to apply that. So first I have negative 6 distributing into my parentheses. Negative 6 times 2 is negative 12. Negative 6 times negative 3 is positive 18. So I have positive 18 or plus 18i. On number 2, I'm going to distribute the 1, and then I'm going to distribute the negative 4i. So double distribution, or often called FOIL. When I do that, 1 times 2 is 2. 1 times negative 8i is negative 8i. Negative 4i times 2 is negative 8i. Negative 4i times negative 8i is positive 32i squared. But, as we just showed, I squared is negative 1. So I have 2 minus 32 minus 16i. So I have negative 30 minus 16i. On number 3, again, I'm going to double distribute. 4 times 3 is 12. 4 times 2i is 8i. Negative I times 3 is minus 3i. Negative I times plus 2i is minus 2i squared. Again, I squared is negative 1. So negative 2 times negative 1 is plus 2. And I have 12 to go with that. And then I have common terms of I. So 8i minus 3i is plus 5i. And 12 plus 2 is 14. So 14 plus 5i. Complex conjugates. Complex conjugates are complex numbers with equivalent real parts and opposite imaginary parts. For example, 2 plus 3i. To find its conjugate, its complex conjugate, I keep the real part, 2, and I change the sign for my imaginary part. Why we do that, we're about to go through. Finding the product of the following complex conjugates. On problem 4, once again, I'll do FOIL. 3 times 3 is 9. 3 times negative 9i is negative 27i. 9i times 3 is plus 27i. And 9i times negative 9i is negative 81i squared. The first thing we note, the imaginary parts cancel each other out. And those were really the only imaginary parts because I squared is actually negative 1. So negative 81 times negative 1 is plus 81. So I have 9 plus 81, which is 90. On problem 5, same approach. 12 times 12, 144. I won't even bother writing in the I terms because positive 60 and negative 60i cancel each other out. So then I have minus 25i squared. Again, I squared is negative 1. Negative 1 times negative 25 is positive 25. So it's 144 plus 25, or 169. Simplifying expressions. We can use the properties of squaring I or using complex conjugates to get rid of imaginary numbers in our denominator. So here, multiplying anything by 1 does not change the number. So it's how you choose the 1 that you multiply by. Here I've chosen I divided by I. Anything divided by itself is 1. So now I'll multiply through the top. 3 times I is 3i, plus 5i times I is 5i squared. On the bottom, 2i times I is 2i squared. Again, we know that I squared is negative 1. So this becomes 3i minus 5 divided by negative 2. When we write complex numbers, we're going to put the real term first and the imaginary term last. So we'll rearrange this to be negative 5 plus 3i divided by negative 2. And of course, this actually means that both parts, the negative 5 and the 3i, are being divided by negative 2. So here we'll have negative 5 divided by negative 2 is positive 5 halves. And positive 3 divided by negative 2 is negative 3 over 2 for the I term. Number 7, same approach, I over I. I'll let you work through that one as a practice. On number 8, now we're going to use those complex conjugates to get rid of my I terms in my denominator. So, my complex conjugate will be the same real number and the opposite imaginary number. Again, any number divided by itself is 1. So on the top, I need to FOIL, or double distribute. So 1 times 3 is 3, 1 times 2i is 2i. I times 3 is 3i. I times 2i is plus 2i squared. On the bottom, again, the middle I terms will go away, but we still have 3 times 3, which is 9, minus 2i times 2i, which is minus 4i squared. I squared is negative 1. So, 2 times negative 1 becomes negative 2. Negative 4 times negative 1 becomes plus 4. So on the bottom of our fraction, 9 plus 4 is 13. On the top of our fraction, 3 minus 2 is 1. And then I combine like terms for my I. I have 2i and 3i, which is 5i. Complex conjugates work for any real part in the front. Square root of 2 is a real number. So we will multiply both the top and the bottom of this fraction as the square root of 2 minus 1i. 7 times the square root of 2 is 7 radical 2. 7 times minus 1i is minus 7i. Square root of 2 times itself is 2. Positive I times negative I is negative I squared. Again, I replace I squared with negative 1. So 2 minus negative 1 is 3. And on the top, 7 radical 2 minus 7i. That is the end of day 5. Thank you.